Hello, I'm Ron Hughes, Senior Consultant for the Reliability Center in Hopewell, Virginia. This is a presentation on recurring thermocompressor cone failures that are occurring at a paper mill in Oklahoma. This analysis was done using the PROACT methodology and documented using the PROACT software. First, let's look at some of the facts of the failure. Alright, here's the thermocompressor cone. Now what this component does is it takes steam from the powerhouse portion of the paper mill and sends that steam to the paper machine in varying degrees of quality and quantity based upon the requirements of the paper machine during the paper making process. Now this is a new system that has been started up for approximately 2 months prior to the initial incident. The initial incident occurs at this gauge port. Now this is a field installed gauge port. It's a 3/8 inch threaded half coupling that they're using for a thermal weld. And what happens is a crack develops in the fillet weld of the thermal weld, goes all the way around it, and propagates into the base material of the thermocompressor cone. Now this occurred approximately 2 months after startup. So they change it out with a like component. This time they leaded this gauge port out in an attempt to fix the problem. But what happens now is after only 9 days, a crack develops in the seam weld of the thermocompressor cone, goes in this direction towards the large end to the toe of the seam weld, and propagates into the base material. Then it goes in this direction right down the center of the weld and makes this big Y pattern. And this is what the two failures look like. Alright, here's the first failure. There's actually a hole here and a crack that goes all the way around, and you can see where the crack propagates into the base material. Over here, here's the second weld. The crack actually starts here. This is the initiation point in the straight area. And it goes in this direction to the toe of the weld and into the base metal, and then right down the center of the weld and makes this big Y pattern. Now this is very unusual to me. The weld should structurally be the most sound part of this component. So how can the crack go down the center of the weld and then into the base material? I'd be happy if the initiation point was over here in the toe of the weld, but the initiation point turned out to be over here in the center of the weld. So these are some answers that we're going to have to find. Okay, let's look at how we analyze this problem. We have reoccurring thermocompressor cone failures. Since we have two failures, that makes this chronic, therefore reoccurring. And we've got two failure modes, known failure modes. The welds have failed, and the base material has failed. And we have to account for both of these in order to solve this failure. So we ask the question, how can the welds fail? Well, we've got two welds. We've got the field weld that was made on site for the 3/8 inch threaded half coupling, and we've got the shop manufacturer's weld. Now we do 100% RT on the welds, and obviously they failed. And we asked ourselves, okay, we'll start with the 3/8 inch threaded half coupling. That was the first failure. How can that happen? And we say, okay, standard defects in the welding industry. Standard defects include cracking, inclusions, incomplete fusion, lack of penetration, porosity, and undercut. Okay, now I really don't need an RT to see the crack. I do that by visual examination, verify it. The outcome is, okay, cracking is evident by visual examination. And if we look at it, we can look at the crack closer. And here you can see it. Now aesthetically, this is a very ugly weld. However, it is fully fused and it is fully penetrated. So it should have held. It didn't hold. So we're going to have to account for that. And we, of course, we're looking at how the crack propagates into the base material. But when we get over here and we start looking at this, let's make this a little bigger. If you notice all the welds pattern. Also notice the coloration, going from a straw color to a deep purple or black color. Now this tells me, and I'm going to end up proving it, that this was either welded with too much heat or it was welded wet, which I sincerely doubt. There's the hole I was talking about. Okay? This right here is the RT. This is actually metallographic analysis. And this shows the crack edge here. And it follows the diagonal edge of the heat affected zone. So it's at the fillet. Now, we didn't cut this out. We went over with a ball peen hammer and just basically tapped it and it popped right out. And when I look at this, just looking at this, coloration tells you a lot. Going from this mottled gray color to a sharper crystalline color, this tells me this was probably never stress relieved, and we're going to end up proving that also. Okay, moving right along. So the field weld is definitely defective. Okay. Now we did look in the RT and we found no inclusions, no incomplete fusion. It's fully penetrated. There's no porosity in the weld, and undercut is evident by visual examination. How can we have cracking? Okay, whenever you have a component fail, it typically fails in typically a combination of these 4 reasons: erosion, corrosion, fatigue, and overload. Now we visually inspect the weld. There is no evidence of erosion in the weld. Also, there is no evidence of corrosion in the weld. Now notice here we got fatigue. Continue at fatigue under manufacturer shop weld defective. That means the logic below here is going to be identical to what we're going to see over here in the manufacturer's weld. But we go in and we RT the weld, and what we find is we have indications of both high cycle and low cycle fatigue. And we're going to look at some of our verification proof here. And what you see here, this again is metallographic analysis. This is a single branch crack. Over here you can see the crack steps. Now what it's doing is, you see these lines in here? These are actually sulfur inclusions. And the crack is stepping along the weak points. Sulfur inclusions are like voids in the metal. And it's actually stepping along these weak points. And also what you see here is martensite. Now this background martensite tells me it was never heat treated. We'll start with that. The only way you can have this martensite on the surface of the weld is in the crystalline structure during the welding process. You go from what is known as body center cubic to face center cubic. Now what happens is the carbon atoms in the center of the crystal, the metallurgical center, are migrating from the center of the crystal to the surface of the crystal. And when they settle on the surface like that, they form martensite. Martensite is very, very hard. And this is a good picture of the tempered martensite, where it has gone from body center cubic to face center cubic. Okay, so fatigue is verified. Obviously it's overloaded. The crack itself tells you that it's overloaded, and you notice again continue at base metal defective, which we're going to explore further over on the base metal section of the failure modes. Okay, so that answers that. Now let's go over here and look at undercut. Undercut is the welding process itself. Undercut is evident by visual examination. So how can we have undercut? Well, either the weld's made properly and we have undercut, or the weld's not made properly. And obviously the weld is not made properly, or we wouldn't have undercut. Also, we do micro and macro examinations, and we can see the defects in the weld. And the defects is the weld has a crack, an obvious undercut at the toe of the weld. In addition, the RT indicates secondary cracking in the weld. Okay? That means the weld is made improperly. Well, how can that be? Well, either the welder's not qualified or the technique is defective. We checked the welder's qualifications and certification. He is certified in accordance with ASME Section 9, so he's a certified welder. The technique is definitely defective, so we look at that examination again, and this is what we find. We can readily see the undercut, and we can readily see the cracking, and we can also see now and know for sure that it's been welding with too much heat. What has happened here, because of all that heat that we see, the weld's been welded at about 1,000 degrees Fahrenheit, never stress relief. Now here we say didn't follow procedure. We're actually being politically correct here. The welder didn't actually have a procedure. We interviewed the welder, and what we find is, he was told, okay, you know how to install a thermal weld, go out there and install one using your experience and best practices. So that's exactly what he did. He went over and he selected an E7018 rod, and of course he installed the thermal weld with a one-hander and just put it in. So he made the weld without a formal weld procedure specification. So we say didn't follow procedure, didn't actually have a procedure, and we say, okay, no heat treatment, stress relieve the heat affected zone. And we look at that, and obviously from what we see in our microscopic examination, we can tell that there was no heat treatment in the heat affected zone. We actually did put the material in a Texas analyzer to see what it was, and we found, and we're going to find that it's actually the wrong material for the service. But here when we look at it, metallographic analysis indicates that the base metal microstructure, regardless of whether it's near the weld or not, looks like tempered martensite. And like I said before, this is a sign it's been heated above 1,000 degrees Fahrenheit with no subsequent heat treating to stress relieve the heat affected zone. So that answers that. And that takes care of the field weld. Now let's go look at the manufacturer's shop weld. Alright, again we have the same welding defects. Inclusions, incomplete fusion, lack of penetration, porosity, undercut, and cracking. Now notice over here we got inclusions, continued base metal defective. Okay? Now we do the metallographic analysis and we see the inclusions. Sulfide inclusions were found in the material, and the crack steps along the path of the voids, that's the weak points, created by the inclusions. And you can actually see the inclusions very clearly in the x-ray. Here's the background martensite. And when we go over here, you can see the inclusions. This is scanning electron microscope analysis here. You can actually see the inclusions. They look like voids in the metal, and those are weak points in the metal. And of course the crack is seeking the path of least resistance, which is the voids. Okay? Now cracking, again, cracking is evident by visual examination. But let's look at incomplete fusion here. We actually do have some incomplete fusion in this weld. Okay, so we RT the weld and we look for areas of incomplete fusion, and there are some areas that are not fully fused. And if we look at our x-ray, here we go, we can see the incomplete fusion here. There's no grain boundary here. That's what that is. Okay, and of course this is the other side of that particular weld. So there is some incomplete fusion in this weld. Okay. Let's check cracking again. How can we have cracking? Cracking is evident. Erosion, corrosion, fatigue, and overload. Now again, our x-ray shows that we have not only fatigue, but we have two types of fatigue, both high and low cycle fatigue. And again, we go over here. This is the shop weld. Now what you see here, these are ratchet marks. Ratchet marks are absolute proof of high cycle fatigue. And we go over here, we see that the crack is very, very flat. Again, this is scanning electron microscope. And there is no sign of ductile or brittle overload. Now what this tells me is the crack goes all the way through the weld and all the way through the base metal. So it is propagated entirely through the component. Now here, these are striations here. These are what we call fatigue striations. Now the fatigue striations occur at low cycle fatigue. They have high amplitude, low frequency. Fatigue striations prove low cycle fatigue. So the striations prove low cycle fatigue, and the ratchet marks prove high cycle fatigue. Ratchet marks occur when we have overlapping fatigue planes. Okay, so we've proved that we have two types of fatigue going on, and we're going to have to account for both of them. Alright, so we have the two types of fatigue. We have excessive vibration, which is high cycle fatigue, and we have thermally induced, which is low cycle fatigue. So we've proven both, so how can we have high cycle fatigue? It's either mechanically induced vibrations or process induced vibrations. Okay? So we walk the system down and we start taking some sound level measurements, some dB readings. And what we're looking for is we're looking for indications of high cycle fatigue. The dB levels range from 98 to 127. It's like standing next to a jet engine. These high levels is 126, 127. They were achieved right, or taken right at the thermo-compressor cone. Now when we look at the piping supports, which you're going to see, we note that not only are the piping supports adding to these dB levels, but because of the way the piping is configured, I have a question about the vena contracta, which is the point of highest velocity at lowest pressure in the design of the thermo-compressor cone itself. And this, of course, is the ISO where we walk the system down, and we're going to be taking all the dB levels at all these strategic points. Okay? So we have mechanically induced vibrations. Our decibel readings tell us that. Either we have inadequate piping supports and inline components, or we could have had like resonance from outside sources, like the paper machine. We actually rang the frequencies, the required frequencies, the bases and stuff, to look for resonant frequencies, and we couldn't find any. But let's look at the piping and supports. So we inspect the piping and support system, and this is what we find. During the walk down and visual inspection of the system, it was noted that several of the trapeze hangers were not supporting anything. The piping wasn't resting on the hangers. Some of the variable spring can hangers were bottomed out, and we actually had stud assemblies that were broken. And this is what the piping support system looks like. This is the stress ISO. And we go through and we note where the spring cans are bottomed out, which stud assembly is broken, where the trapeze hanger is not supporting the pipe. As a matter of fact, the location of the trapeze hangers is not supporting pipes right here at the thermo-compressor, which is really bad. And this is definitely contributing to the mechanically induced vibrations that we're seeing. That's the physical root. Well, how can that be? Well, we could have a system support design error, valves contributing to the mechanically induced vibration, or a thermo-compressor design error. Notice we got continue at vendor didn't understand the operating environment. And we'll talk more about that in a little bit. First thing is the C/V across the valves. We actually looked for problems with the velocity across the valves, and we couldn't find any, so these are not contributing. We actually checked the C/V, and all velocity and pressure drops are normal and not contributing to the observed mechanically induced vibrations. Now, we've already talked about the piping supports, obviously, but we have a piping support system design error. Let's talk about that. We're going to talk about interviewing the support designers to determine how the system was analyzed for the existing design. Now, the pipe fitters are actually the designers. There is no formal engineering design for this system, or even a design review. Now, what the pipe fitters have done is they've used the Franklin book, the blue book. This is the little pocket manual the pipe fitters use so they can figure out takeouts for fittings and, you know, how to hang piping, you know, every so many feet based upon the size of the piping, so close to a bend, so close to an inline component, etc. Now, the Franklin Blue Book is for water lines. This is a steam line. Now, it's totally inadequate for determining how to hang a steam line. So what they should have done is they should have done a stress analysis, a detailed stress analysis on the system itself, and designed it as a high energy steam line, and they didn't do that. So the existing system is contributing significantly to the mechanically induced vibration and the high dB levels that we have observed. So that answers that question. Now, how can that be? Obviously, no formal detailed design or engineering design review performed on the support system as required. So that answers that question. TC cone design error. So we interview the manufacturer of the TC cone and we see, you know, how was this thing designed? And what we find is the manufacturer was never given any details other than the required pressure drop of the thermo-compressor cone, or specifications on the TC cone. So when we look at it, when we further analyze it, we find that the vena contracta is mislocated and definitely contributing to the failure under investigation. So that answers that. Okay? So let's go over here and we're going to look at process-induced vibrations. Now here we just reviewed pi data and of course operational histories, and we're going to be looking for evidence that the process is causing these vibrations. And what we find is common practice to adjust speeds, temperature, and steam pressure in order to meet the customer requirements for varying grades of paper. These operational changes are definitely causing process-induced vibrations. Okay? So again, how can that be? Well, we're operating at the critical frequency of the pipe. So we determine the critical frequency of the pipe, and we find it to be 540 hertz, and we find that we're operating in that range. So that's definitely contributing. And how can that be? Well, we're operating at variable pressure and flow changes because what we're trying to do is meet the requirements for making paper. And these operational changes are not accounted for in the original design. Remember, this is a new system. Okay? So that takes care of the understanding of where the high vibrations are coming from. Now let's look at thermally induced or low vibrations. So where could that be coming from? We say, okay, it's either process-related changing steam demands, which we have, excessive startups or shutdown. We review pi data and operational histories. We don't have excessive startups and shutdowns. Condensate in the system, or we have fluctuating temperatures and pressures coming from the powerhouse. When we look again at the pi data, I love pi data. When we look at the pi data, we find that the pressures and temperatures coming from the powerhouse are all within range and all very stable. But our pi data shows that we have a lot of process-related steam demand changes. And the reason for that is the control valve positioning between the third and fourth sections of the paper machine is constantly repositioning itself in order to meet plant requirements. So we're running at what we call high and low turndown ratios. A turndown ratio, of course, is how fast you take the paper off the machine, and of course that varies based upon the quality of paper that you're making. And we're varying these operating speed to meet plant requirements. That's definitely contributing to low cycle fatigue. Condensate in the system. Well, we go do a real fancy verification here. We go over to a drip leg, open the drain valve, see if water comes out. Guess what? Water comes out. We've just proven we have condensate in the system. So the question becomes, how can I have condensate in the system? And there's 4 potential sources for this. It's either condensate from the desuperheater. When we check that, there is no condensate coming from the desuperheater. It either entered through the 65 psi steam supply, or it entered from the 600 psi steam supply. Again, checking our drain valves, we find that it's not coming from either one of those places, but it's definitely coming from condensate return from the steam trap system. When we go over and we check the steam trap system and look for evidence of condensate in the system, we find the drains are impeded by back pressure and on the traps. So there is condensate in the system. This proves that we definitely do have condensate in the system because the drains aren't draining. Okay? They're impeded by back pressure. So how can that be? This is pretty standard in industry. We see it everywhere. The drains are impeded by back pressure because of the steam trap design deficiency, because the original design for the steam trap system is inadequate for the current design of the new system. And what we do here, of course, we compare the existing design of the steam trap system and determine if it's adequate for current plant requirements, and we find it's not. The current design is inadequate because the steam supply has been modified and the steam trap system was not taken into consideration during the modification. So therefore it wasn't modified, and therefore it's not accounted for under the current configuration. Alright, let's move up here. And we're going to minimize this and go over here to base metal failures. Alright, how can I have base metal failures? Again, we're at the component level: erosion, corrosion, fatigue, and overload. Now notice over here under fatigue, we prove we have fatigue. We RT the weld. We see both signs of high and low cycle fatigue. This is the actual manufacturer's weld again. And we're back to the scanning electron microscope analysis. And metallographic analysis. And we see both evidence of high and low cycle fatigue. Alright. Overload. Base metal defect. Okay. So we use a Texas Instrument analyzer because we want to verify what the base metal actually is. And we're going to look for the elemental constituents of the base material. And we find that the TC cone is manufactured from ASTM A516 grade 70 material. Now this is a pressure vessel material. This is a good material, but it's not the right material for the service that we're seeing. For the service that we're seeing, we need something with more chrome and more molybdenum to give it higher strength at a higher temperature. And of course, here's the results of our analysis from the Texas Analyzer. These are our elemental constituents, and this, based upon the percentages, we find that this is definitely ASTM A516 grade 70 material. Okay, not the right material for the service. Okay, base metal defective. How can that be? Well, it's either not made per specification or made per specification, or not specified correctly. Excuse me. It's either not made per specification or it's not specified correctly. In actuality, let's talk about this just a little bit, even though we got an X on it. We compare what was specified on the purchase order with what was originally supplied by the manufacturer. Okay? So the purchase order really doesn't specify a material specification for the TC cone. All it does is it gives a pressure drop criteria. Now, the owner of the plant is depending upon the manufacturer of the TC cone to spec the correct material themselves. So the manufacturer made the cone out of, like I said, ASTM A516 grade 70 material, 5/16 of an inch thick. Okay. Now this is fine for most applications, but it's not fine for this particular application due to the pressures and temperatures that we were seeing. So what he assumed was, okay, this worked at other places, it will work at this plant also. And that's a bad assumption. Okay, so it's not specified correctly. We do a finite element model on it. And what we find is that the material used is not adequate for the service that we're seeing. And let's look at this. Okay, now this is where we're modeling it, and what we do is we model it in 9500 plate elements. Of course, the areas of lavender are areas of very low stress, and the areas of red are areas of very high stress, and we can look at the deflection shape. And this is what we found in our model. Now this is at 540 hertz. This is the natural frequency of the pipe. Now right here is where our crack is. This is where our crack initially developed. And as you can see, look at the flexure in the model. And then we come over here to 777 hertz, which we're also seeing. Look at the model flexure. And that accounts for our Y crack. Okay, and then of course we went over, this is the stress strain diagram and the number of cycles that we're using. You know, we're figuring everything out in our model, and we compare what we're going to recommend, which is a 1/2 inch thick chromoly material, to what was actually supplied, a 5/16 of an inch carbon steel material. And we determined that our 1/2 inch, using our model, our 1/2 inch chromoly plate will definitely work for the situation that we're trying to operate in. Okay? So not specified correctly, because the vendor didn't understand the system operating environment, and we have inadequate component specifications for the Thermo-Compressor code. Okay, this is the base metal failures. Let's look at these. Okay, how can the base metal fail? Erosion, corrosion, fatigue, and overload. Again, notice fatigue. Fatigue occurs over at the welding where we've manufactured the cone and has already been covered. But it's definitely been overloaded. So we, just by visual examination, verify overload. And we can see from my pictures here, it's obvious that the weld is cracked and definitely overloaded. And when we get over here, this is the initiation point. Now, the way we know this is the initiation point is we actually look at the chevron marks when we cut this thing up, and you're going to see where we cut it up. And the chevron marks go in this direction, and they go in this direction. Now, where the chevron marks come together, the arrows come together, that's the initiation point. And the initiation point is right in the center of this very straight crack here. So that's when the failure started, and it propagated in that way, and it propagated that way. Okay? So it's definitely overloaded. So how can it be overloaded? Base metal defect. Well, again, we go in and we look at the Texas analyzer and see what we got, and our finite element model showed us what we needed, which was chromoly steel versus the carbon steel that was supplied. But we also did some Rockwell hardness testing. So we do Rockwell hardness testing to determine the base material's hardness and whether or not it was stress relief. We're going to look at the crystalline structure, and we show that, you know, we did all right. The Rockwell hardness test proved that the material in the center of the weld and the base metal was softer than the material on the surface. This indicates the presence of martensite on the surface of the material caused by the crystalline structure of the material's piping going from body center cubic to face center cubic. This proves that the material was never stress relieved. And here's where we did the hardness testing. We actually cut it up into several plate elements. And we're going to measure the hardness both on the surface and the center. And of course, this is SEM analysis. And what we find is the material is very hard on the surface and very soft in the center, which is what we expect. And that also proves that the base material is defective for the surface. So the base material is defective. Well, either it's not made per specification or it's not spec'd correctly. Well, let's look at this. Okay, again, the manufacturer was just told, make me a thermal-compressor cone with a certain pressure drop, and he used his best judgment for the material that should be used to manufacture the cone, which turns out to be the wrong material. In actuality, he has no specification, so it is not spec'd correctly. So since it's not spec'd correctly, how can that be? Well, the vendor didn't understand the operating environment because the plant owner did not provide him the proper operating environment specs. And also, we have inadequate component specifications. In actuality, he had none. Okay, so let's look. That completes the analysis, and we'll just give you an idea what the tree looks like. Okay, it's actually a fairly large tree, as you can see. And we have lots and lots of root causes here, and we have to make recommendations that will eliminate these causes, these identified causes. So we're going to make recommendations for solutions that will take care of those causes. Now, I already told you what the event was. That's the event summary, but let's look at the findings. The physical attributes of both failures are the result of defective welds and inadequate base metal materials that resulted in failure due to both high and low cycle fatigue during plant operations. Both weld breaks, the 3/8 inch threaded half coupling fillet weld and the thermo-compressor cone seam weld, propagated along the sulfur streak in the base material. In addition, not only was the base metal made of less than optimum material, but also the wall thickness was too thin to carry the operationally induced high vibration loads caused by inadequate design of the pipe support system and improper fabrication of the thermo-compressor cone. The latent issues that cause physical failure are attributed to design and welding errors resulting from inadequate / no formal detailed design or review. The lack of detailed specifications resulted in an inadequate thermo-compressor cone and steam system design. So let's look at our recommendations here for our roots. So for example, this is a physical root cause, and I won't go into all the detail, I'll just give you an idea. The base metal is defective, that's a physical root, so we're going to make a new thermo-compressor cone from a chromoly steel of the correct grade and give it additional strength at operational temperatures and pressures. And this tells you what the new material should be. Inadequate component specs, a latent root cause. We're going to create a new specification detailing the requirements for the new thermo-compressor cone, and we give all the detail for that. No requirement for weld inspection. We're going to add necessary weld inspection testing requirements and the detail for that. No heat treatment. We're going to stress relieve all welds by heat treating in accordance with ASME section 9. Drains impeded by back pressure. This is a steam trap system. We're going to reconfigure the design of the steam trap system to remove back pressures that are preventing adequate drainage. Original design, the trapping system is inadequate, and we give the details for how to redesign it. Operational changes not accounted for. Based upon the new plant system, we're going to correct the operational procedures to meet new plant requirements, and we give the details for that. No formal detailed design or engineering review. We're going to modify existing piping and supports per the outcome of the stress analysis by an independent resource, and we give them details on how to do that. Okay. Well, that concludes this presentation. If you'd like more information on the PROACT methodology or the PROACT software, or even on root cause analysis in general, don't hesitate to contact the Reliability Center. They're true experts in this type of analysis. Thank you. Have a great day.